All right, hello everyone, and welcome to our 9.8 lesson for AP Chemistry on voltaic and electrolytic cells. Today we're going to be talking about how electrochemical cells rely on different components that work together to control electron and ion flow. Voltaic cells use spontaneous reactions to produce electrical energy, while electrolytic cells use external energy to drive non-spontaneous reactions. In all electrochemical cells, oxidation is going to occur at the anode and reduction is going to occur at the cathode. All right, so in this lesson, I really want you to focus on the difference between these two electrochemical cells that we're talking about. I know we talked a little bit about electrolytic cells in our previous video, and if you remember, those were reactions that were not spontaneous, and by introducing electrical energy, it's going to drive that non-spontaneous redox reaction. So in an electrolytic cell, that's going to be a positive delta G, and we are adding electricity to this reaction to then kickstart it so the electrons start flowing and then that reaction can occur. Now with a galvanic or a voltaic cell, this is going to be a spontaneous reaction. So this is going to be a negative delta G. And by spontaneous, I mean once I put in these electrodes and I connect them with a wire, these electrons are going to start flowing without any external energy source. And because that chemical energy is flowing, we can actually capture that with some sort of battery or, in this case, light bulb. We can also hook up what's called a voltmeter and measure the amount of electricity flowing through that system. Okay, so first difference is spontaneity. Electrolytic, non-spontaneous, that we are making spontaneous with an energy source, and galvanic or voltaic cells is a spontaneous reaction. We are just capturing some of that chemical energy and turning it into electrical energy. So that's our first difference between the two. Our second difference is setup. Now, this one's drawn a little odd, and AP Chemistry typically doesn't draw it like this. But in a galvanic or a voltaic cell, you're going to have two separate solutions. They're typically going to be in different containers. This one kind of shows it in one container, but it does still show a partition. So in a galvanic or a voltaic cell, these two half reactions are going to be occurring in different or separate solutions. And then they're going to be connected by what is called a salt bridge, which we will talk about later in the video. And so that is the setup for a galvanic cell. In an electrolytic cell, it's all happening in the same solution and there is no salt bridge. So there's no need to divide the two solutions separate from each other because we only need one solution in order to kickstart that electrolytic cell. The other difference I want you to notice is the charge of the anodes and the cathodes in the different electrochemical cells. We can see in the voltaic cells, our anode has a negative charge and our cathode has a positive charge. But in the electrolytic cell, it's the opposite. The anode has a positive charge and the cathode has a negative charge. And that has everything to do with whether it is spontaneous or not spontaneous. So because our voltaic cell is spontaneous, the anode is essentially very negative, producing those electrons, and then it's going to move to that positive side, where in an electrolytic cell, that battery or electrical source is literally pulling the electrons from the anode, so it creates a positive electrode. And now let's talk about our similarities between the two. The first one is that the electrons always flow the same direction. They always flow from the anode to the cathode. I like to think about an AC unit, so it always goes from A to C or anode to cathode. So that is the same in both. The other thing that is the same in both is what happens at the anode versus what happens at the electrode. So at the anode will always be oxidation, and at the cathode will always be reduction every single time, no matter what type of cell you have. All right, so quick review of all of that. Both electrochemical cells are going to contain two solids electrodes. They're going to have the anode and the cathode. Remember, the anode is always where oxidation occurs, and the cathode is always where reduction occurs. And you can remember that with the mnemonic an ox and a red cat. The sign of each electrode is going to depend on whether it's a voltaic cell or an electrolytic cell. If you have an electrolytic cell, remember you are putting in the energy source that is kickstarting the reaction. So when you add in, let's say, a battery, it's going to pull the electrons from one side, which is why the anode is positive, and it's going to push those electrons towards the cathode, which is why it's negative. However, in a galvanic or voltaic cell, those electrons are flowing on their own. So because oxidation is happening at the anode, all of those electrons are coming from the anode, which is why it's negative, and then it's going to be attracted to the positive cathode. All right, so let's go ahead and run through how to do a voltaic cell. And before we do that, I want to go through a chemical reaction, and I want to practice identifying what's being oxidized and what's being reduced to get our half reactions, or what's going on in each half cell. So first, let's assign our oxidation numbers. So we know zinc is a pure element, so it's going to have an oxidation number of 0. Copper 2 plus is an ion, so it's going to be the same as its charge, or +2. Elemental copper would be 0, and Zn2 plus will be +2. So here we can see that zinc is going from a 0 to a +2 oxidation number, which I know is losing electrons. If you do not know that off the top of your head, you can always write it out. That always helps me sometimes. So if I have solid zinc becoming Zn2 plus, I can see I'm not balanced charge-wise. So if I were to add electrons to balance this out, I would need 2 electrons on my product side, which means I am losing 2 electrons. And if you remember, oil rig, oxidation is loss, reduction is gain. So since I'm losing electrons, this is oxidation. So this would be the reaction occurring in one of my half cells. And then in the other half cell will be the reduction. But again, if you did not know that, let's go ahead and start with our species from our equation. So as you can see, we're not balanced with the charge. So if we add in 2 electrons in the reactant side, now we have a charge of 0 on both sides. So here you can see that the electrons are a reactant, which means we are gaining electrons, which is reduction. And if you remember from earlier in this video, oxidation is going to occur at the anode, and reduction is going to occur at the cathode. So just from that equation there, we can figure out what's being oxidized, what's being reduced. We can figure out the half reactions that are going to be occurring in each half cell, and we can tell each other what electrode that is happening at. And we know that the oxidation of zinc is happening at the anode, and the reduction of copper is happening at the cathode. All right, so some of you may have been looking at this equation and thinking to yourself, well, why is zinc going to donate its electrons to copper 2 plus to form solid copper? Like, why wouldn't copper donate its electrons to form solid zinc? And the answer to that is because of the reactivity of our two metals. Now, because zinc is more reactive than copper, zinc is more likely to donate its electrons than copper is, which is why zinc is the one being oxidized and copper is the one being reduced. In other words, zinc is higher on the reactivity series, so is more readily losing electrons, whereas copper is less reactive, therefore it's more likely to readily gain electrons. And because electrons naturally flow from a more reactive metal to a less reactive one, this reaction occurs spontaneously, giving the negative delta G and then producing that electrical energy. All right, so to create our voltaic cell, we're going to have our two half cells, and in each half cell will be an aqueous solution of ions that consist of the metals that form in the overall equation, as well as a spectator anion. In this case, we're going to be using sulfate. So in one of our half cells, we're going to have zinc sulfate, and the other one, we're going to have copper 2 sulfate. So both of them have our metal cation and the sulfate anion. Then to each of our half cells, we're going to add in a piece of metal that coordinates with the metal cation. So on the left half cell, we're going to add in zinc metal. And then on the right half cell, we're going to add in copper metal. And from that point, we're going to add a non-reactive metal wire to both of the electrodes. So once we add that wire and connect those two electrodes together, because this is a spontaneous reaction, those electrons are going to start flowing from our anode to our cathode. All right, let's break down what's actually happening in this voltaic cell. So we've connected the two with a wire, and we know our zinc is what's being oxidized. So zinc is going to turn into a Zn2 plus ion and 2 electrons. And as you can see, some of that zinc anode deteriorated a little bit because over time we're going to lose mass because solid zinc is turning into Zn2 plus aqueous and 2 electrons. So that's going to lose mass over time. So now we have an extra Zn2 plus in solution, and we have our 2 electrons that are now going to travel to our other electrode, which is our cathode. And now we have these electrons in this cathode, and we know that our Cu2 plus, which is oppositely charged, is going to be attracted to those electrons. And once those combine, it's going to form solid copper. And that solid copper is going to plate onto that cathode, which is why we use the little phrase, the cat gets fat. And that's just a fun little reminder that the cathode is going to gain mass over the time and the anode is going to lose mass over time. All right, so now we're at the point where one zinc particle broke apart into Zn2 plus and 2 electrons. Those electrons traveled over to the copper cathode, and then a copper 2 plus ion reacted with those 2 electrons to form solid copper. So now I want you to look at these two solutions and tell me if you see a problem. I will tell you that there is a very big problem. There is a very big problem because, as you can see, these two cancel each other out. These two cancel each other out. These two cancel each other out. But we are left with a 2 plus charge in solution. We cannot have a charged solution. So this is going to be a 2 plus solution overall. And in this solution over here, you can see that these two cancel out, these two cancel out, but we're left with a 2 minus charge on our solution. So as you can see, this is not sustainable. So what do we do? This is where the salt bridge comes in. So when we introduce this salt bridge, the salt bridge is going to have an ionic salt that is not going to be reacting. It's just going to be essentially spectator ions, but those ions are going to flow into these solutions so that we can keep our overall 0 charge. So once that copper plates onto that cathode and we lost a Cu2 plus ion, 2 sodium ions are going to come from the salt bridge, come into the solution, and then they will give us our overall zero charge like we had before. Same thing with our other half cell with the zinc. Because we added in that zinc 2 plus into solution, we're going to move a sulfate ion into that solution, and now we're back to a neutrally charged solution. So that is the importance of a salt bridge. All right, so let's review everything we just did to fully make sure that we understand what's happening. So here is our voltaic cell. We have zinc sulfate in solution on the left half cell, and we have copper sulfate on the solution on the right half cell. So in the left half cell, we know this is going to be a zinc electrode, and the right, this is going to be a copper electrode. In the zinc sulfate solution, we're going to have Zn2 plus in solution, as well as SO4 2 minus in solution. And then in our right half cell, we're going to have copper 2 plus in solution and SO4 2 minus in solution. And then our salt bridge, we can see we're going to have sulfate ions as well as Na plus ions. So now when this wire is connected to the two electrodes, we know that zinc readily loses electrons. So let's just use one zinc atom as an example. That zinc atom is going to turn into 2 electrons and an added Zn2 plus ion. Now, because we added Zn2 plus to the solution, our sulfate ion is going to come from the salt bridge and add into solution so that we still have a neutrally charged solution. Then our electrons are going to flow to the cathode, which is positively charged. And they're going to be on the cathode ready to react with the copper 2 plus ion. Now those are going to combine to form solid copper, which is then going to plate onto that copper electrode, which is why the cathode gains in mass. But as you can see now, we have a charged solution. So in order to make that neutral, 2 sodium ions are going to come from the salt bridge and into solution. So now we have a neutral solution. And because this process is spontaneous and these electrons are flowing along this wire, we can put something on this wire to either capture and use electricity, or we can measure the amount of electricity. So typically AP will use a light bulb to showcase that it's harnessing the chemical energy and turning it into electrical energy like light, or it can use a voltmeter. So it'll either show a voltmeter with actual numbers on it, or it'll use a V like you see here just to signify that it's just measuring the amount of electric current going through. All right, so let's do some examples with voltaic cells. So a standard electrochemical cell is constructed according to the diagram. A balanced equation and thermodynamic data are provided for the reaction that occurs while the cell operates at 300 Kelvin. All right, so looking at this data on the bottom here, I can already tell that this is a thermodynamically favored solution. You can also assume it's thermodynamically favored because it's a voltaic cell, but if you wanted to double check, or if it was asking you to solve for whether it was thermodynamically favorable, you could always plug that into the delta G equation. And that will give you a delta G of negative 90 kilojoules per mole. So because it's negative, we know it is thermodynamically favorable. So the question says, which of the following claims correctly describes the flow of ions in the salt bridge as the galvanic cell operates? So let's look at the galvanic cell or the voltaic cell and look at what's happening. So from the reaction, I can see copper is going from solid copper to ions, which means I know copper is losing electrons, which means copper is being oxidized. So the electron flow is going to be from copper to silver. So that is going to be the flow of electrons because copper is losing electrons and then silver will be gaining them. So now that we know the flow of electrons, we know that copper is going to separate into Cu 2 plus here, and then it's 2 electrons. And then we know some of the copper is going to come off of the anode. And then since the electrons are coming over to the silver side, we know that the positive Ag plus ions are going to react with those electrons and they're going to form solid silver and they're going to plate onto this cathode. And when we do that, we're losing Ag plus from solution. So if I have Na plus and NO3 minus in my salt bridge, I know if I'm losing Ag plus, I need to replenish that plus charge. So I'm going to be adding Na plus here. And I know on this side, if I am adding in copper with a 2 plus charge, I need to balance that out with something negatively charged. So that means I know my nitrate is going to be flowing into this half cell. So now that we understand that, let's go ahead and look at our options here. Part A says Na plus ions flow towards the Ag half cell as they experience attractions to the electrons that flow through the salt bridge towards the Ag half cell. Now, Na plus ions are in fact flowing towards the Ag half cell, but they're not due to the attractions of the electrons that flow through the salt bridge because electrons do not flow through the salt bridge. So A is not the right answer. B says nitrate ions flow towards the Ag half cell, which we just talked about how that's not true. Nitrate goes towards the copper half cell, so that's not true. C says Na plus ions flow towards the copper half cell, which is false because Na plus ions go to the silver half cell. And then D says nitrate ions flow towards the copper half cell, which is correct, as the electrons move through the wire from the copper electrode to the silver electrode, and that is the correct answer. All right, so here we have another voltaic cell, and it says which of the following substances would be the best choice for filling the salt bridge. Now, the first thing I want to make very clear is the name of it. It's called a salt bridge. Salt bridge. Out of those 4 answer choices, which one is a salt? I'll tell you, the only one that is ionically bonded is KNO3. So D is our only salt, so D is the only one that will work for the salt bridge. However, if you want a more detailed explanation, we know that the salt bridge is intended to provide an easy transfer of charge from one half cell to the other half cell, and that's to avoid excessive charge building up as the reactions proceed. So because we have KNO3, which has K plus ions and NO3 minus ions that dissolve in water, they're able to carry charge into each of those half cells to maintain that neutral solution in both half cells. All right, and here's another voltaic cell example. It does kind of loop in some information that we're going to learn in the next video, but this is a great way to introduce that. So you are given 2 half reactions from a standard voltaic cell, and it's giving you these values for E. And E stands for standard reduction potential. And it is exactly how it sounds. It is literally the potential that something has for being reduced. So a higher E value is going to mean that it is more likely to be reduced. So because 0.34 is more positive than negative 0.76, then we know that copper 2 plus is more likely to be reduced. And so Cu2 plus is going to happen at the cathode. Now, because we know copper is being reduced, we now know that zinc is being oxidized. So in order for this reaction to work, we actually are going to flip this reaction to show zinc being oxidized. And that would change this standard reduction potential to positive 7.6. So then, just a little side note, if you ever had to get the overall standard reduction potential for the entire cell, then you would just add those two values and you would get positive 1.10 volts. All right, so now that we know our two half reactions for our reduction and our oxidation, we can get the overall net ionic equation by canceling out our electrons. So we can see our two electrons will cancel out with these two electrons, and now we can get our overall equation, which is Cu2 plus Zn, and Cu2 plus is aqueous, Zn is solid, and that's going to form Cu solid and Zn2 plus aqueous. And that would be your answer for this question. All right, now let's move on to electrolytic cells. So we know that electrolytic cells are going to have a solution that has a positive delta G, meaning it's a redox reaction that is not spontaneous. It's going to need a surge of energy in order to kickstart that reaction to actually form those products of the redox. So remember, electrons are still going to flow from a wire from the anode to the cathode, just like in voltaic cells. And we also know that the oxidation is going to occur at the anode and the reduction is going to occur at the cathode. And also remember, in an electrolytic cell, there is no barrier. These two electrodes are going to happen right in the same solution with no barrier and no salt bridge. All right, so first let's go over electrolytic cells with molten electrolytes, meaning there is no water. So we know that this specific solution of Na plus ions and Cl minus ions are not going to react on their own to form chlorine gas and solid sodium. However, if we do introduce a battery and allow the battery to move the electrons from one side to the other, that will in fact successfully complete the redox reaction to form chlorine gas and solid sodium. So first let's look at the anode. So the anode is positive here, and we know at the anode oxidation is going to occur. So those chlorine ions are going to lose electrons, and then they're going to form elemental chlorine and give off those electrons. And those electrons are going to flow to the cathode where we have our Na plus ions. And those Na plus ions are then going to react with those electrons to form solid sodium. And the solid sodium is going to plate onto this cathode. Remember, the cat gets fat. Still applies to electrolysis. Now, in electrolytic cells with aqueous solutions, the ionic compound is dissolved in water. So both the compound's ions and water itself are present. And because water can ionize into H plus and OH minus, it can also participate in redox reactions at the electrodes. And that is going to mean that water may compete with the dissolved ions for oxidation and reduction. And as a result, we have to use those standard electrode potentials, or E values, to predict whether the ions for the compound or the water will be discharged at each electrode. So remember, electrode potentials measure how easily a species is reduced, the more positive the E value, that's going to mean a greater tendency to gain electrons. And just a side note, looking at these two equations on the screen here, we can see when water is being reduced, meaning it is gaining electrons, that means we're going to create a basic solution. However, when water is being oxidized or losing electrons, it is going to create an acidic solution. So just keep that in mind. Ever so often that is brought up in College Board questions. In electrochemical cells, the species with the higher or more positive standard reduction potential is going to be reduced at the cathode because it has a greater tendency to gain electrons. The species with the lower, more negative E value is instead going to be oxidized at the anode, meaning its half reaction is reversed, so it loses electrons. In short, reduction happens at the cathode with a higher E, and oxidation happens at the anode with a lower E. All right, and to wrap up this video, let's go through a question on electrolysis. So first it wanted you to draw a particle diagram of what it looked like when lithium chloride was dissolved in water. This is a review from earlier units, but I do think it's important to go over since we're so close to the exam. So when you dissolve lithium chloride in water, you're going to have your Li plus ions and your Cl minus ions. And then it wanted you to orient water around those ions to showcase the partial positive, partial negative ends of a water molecule. So we know oxygen is more electronegative than hydrogen. So because oxygen has the partial negative charge, that's going to be what's attracted to the positive lithium. And then for my negative chlorine, we're going to want our positive hydrogens facing the chlorine. And this would give you full points. Then part B says a student passes a direct current through the solution and observes that chlorine gas is produced at the anode. So we already know that chlorine is being oxidized because it's at the anode. Now we got to figure out what's being reduced at the cathode. And remember, when you have water involved, water can technically be reduced as well. So we need to look at what is more likely to be reduced, the lithium or the water. And that is all about our standard reduction potential. Remember, the more positive the E value, the more favored they are for reduction. And as you can see, water has a higher E value than lithium, which means water is going to be reduced at the cathode.